Yeah. Hi, I'm Richard from Austria. And before starting, I really want to sincerely thank the organizers for putting together such a great workshop. I still have fond memories from my Caltech days where we and the other postdocs would sneak up from Caltech, stay at a Motel 6 and kind of like enter these conferences semi-legally. I can say it's much, much nicer to be an official participant. So thank you for having me. I also appreciate that I'm the last thing that is between you and a nice evening with friends at the beach. So I know the stakes are high, and I will try to make this worth your while. And in order to maybe make this a bit more interactive, I really, as Andreas pointed out, I encourage you to ask questions already during my talk. Please just raise your hand and feel free to interrupt me. I will then repeat the questions so that the Zoom audience can hear it and that we have them also recorded. And I mean this sincerely because I'm here as part of the computer scientist minority, I think. And so I would really like to bring kind of like my ideas across, but I know that our languages sometimes don't match up. And if there's something that isn't completely clear to you and you ask me, then you give me the chance of clarifying it and maybe taking everybody along the way. So really, please feel free to ask questions during my talk. Yeah, the title of my talk today is an infinite hierarchy of multi-copy quantum learning advantages or tasks. And in a way, it is a continuation of the very nice tutorial that we had last week by Andreas. So the long-term visitors here have an advantage by having seen his tutorial. And it's about the power of multi-copy learning protocols. And this is also the talk of today's talk. And I want to motivate it first by briefly presenting you a landscape of known multi-copy learning advantages. And then I want to zoom in on one of these tasks, which is called quantum enhanced learning or Pauli shadow tomography, which was developed by Robert Huang, John Preskill, myself, and also the Google team a couple of years ago to really show that these multi-copy protocols become tractable and they can yield to exponential advantages in a learning context. So this is the baseline. And then the last part, and this also connects to the title, is we set out to generalize this mindset and ask ourselves, are there learning challenges that we can solve with 5 copies, but not with 4? Are there some that we can solve with 7, but not with 6? And so on. And I'm happy to report today that we found an infinite hierarchy of these things. Okay? And then I will give a brief illustration, some transpilation and numerics, and wrap up, and then we're all free to go to the beach. So here's the motivation. It's maybe a bit coarse-grained, but I want to kind of like summarize the landscape of known multi-copy learning advantages. And here the idea is typically in quantum mechanics, we think about linear observables and linear expectation values. We think about preparing a quantum system in a quantum state row. So look at the top. Then we maybe do a unitary evolution to rotate it into some basis that we care about. Then we take a measurement, we get a single shot outcome, and then we repeat this loop enough times to get statistical accuracy. And one thing you learn in your quantum mechanics courses is, in principle, you can estimate every single observable that way, finding the right unitary. Another example that fits into this category is the concepts of classical shadows that Robert is going to give a talk tomorrow, myself and John developed, and Andreas also explained last week, where you use a randomized single copy strategy to jointly predict many low-weight observables. But there are things beyond the reach of classical shadows. Like what about all Pauli observables, for example? And one way to get closer to these difficult tasks is to change the paradigm we take measurements in. For example, we can now envision that we are given 2 copies of the quantum state in parallel on the same quantum memory, and then apply a joint entangling unitary prior to performing the measurements. And if we do that, why stop there? We could mention 3, 4, 5, or all the copies that we care about being presented in kind of like a very, very big quantum memory. And traditionally, this all copy scenario is actually the most explored one in quantum information theory, at least. For example, if you want to do optimal quantum state tomography, the actual first optimal protocol was developed almost 10 years ago and was phrased in this all copy parallel entangling measurement setting. Another example, which excites me, is Scott Aronson's proposal of shadow tomography, where you can really jointly estimate any collection of observables by doing big circuits on all copies. So this is conceptually interesting, but it's very, very demanding to do it technologically, and this is questionable whether we actually ever get there. And so I also am interested in this intermediate regime, and there a lot of attention has gone into the two-copy framework, where you exactly provided 2 copies of the state, you can do an entangling circuit and perform measurements. And an example that kind of like becomes extremely easy here is to compute the purity of your quantum state. We've heard this earlier today when it was about the entropies. You can do a swap test or a destructive version thereof and natively read out the purity with 2 copies, but it's exponentially expensive to do it with single copies. And we have proofs for that by Sita and Chen and friends. So this is an example of a 2-copy learning advantage. It becomes very cheap and easy if you have 2 copies, but exponentially hard in the number of measurements you have to do if you do any single copy strategy. And another example, which forms the core of today's work, is the task that is now known as Pauli shadow tomography. Can you jointly predict all Pauli expectation values, or at least their absolute values, from some measurement data? This also sounds exponentially hard because there's exponentially many of them, but I will show you on the next slide that there's a 2-copy protocol that does it with only very, very few samples. Okay, so this is kind of understood, and the topic of today's talk is what is in between. Is there something that we can do with 3 copies that we can't do with 2? Is there something we do with 4 copies that we can't do with 3? Is there something that we can do with 5, but we can't do with 4? Okay? Are there questions or comments at this point? I don't. Yes, Maxime?
So this all copy setting means that you have a certain number of copies, or that you allow arbitrary unitary operation? Or like how many is all?
Thank you, Maxime. Maxime asks what is the all copy regime at the very end. And this is typically loosely defined. But if you think about learning scenarios, then an important summary parameter is the sample complexity or the copy complexity. How many copies of my quantum state do I need in a learning theoretical sense to get the property I care about, up to a certain accuracy? And in the all copy regime, you're really assuming that you get all these copies that your theoretical algorithm demands in parallel in a huge quantum memory, and then you can do a big entangling circuits on top of them. Did this answer your question? Thanks, Maxime. More questions or comments? Great. Then let me move on to kind of like this vignette challenge that I want to look a bit closer at, because we will use this learning task to generalize it to more and more copies. And this is, I think, today known as Pauli shadow tomography. And there the overarching goal is to jointly, like somehow collectively, learn all possible 4 to the n Pauli observables in an n-qubit system. And for technical reasons, I'm fine with only learning the magnitude and not the sign. You will see this later. But these are 4 to the n different numbers, and your task is to learn all of them. How many measurements do you need? And I want to say something about the hardness of this task. I want to kind of like show that it is hard for single copy strategies, but easy for a 2-copy strategy. And in order to be able to make such a statement, it's convenient to reformulate this overarching goal as an underlying learning challenge. And the learning challenge you should have in mind here is data hiding. If I have n qubits, I can deviously encode an n-trit string, a personal secret, into a mixed quantum state by just perturbing the maximally mixed state in a direction of the n-fold tensor product of the Pauli matrices of these words. So this is a map from n symbols, x, y, or z, to an n-qubit mixed state. And this is my data hiding stage. And then the learning challenge asks for you to buy copies of the state from me. You can measure them any way you want. How many do you need to learn my secret? It's a bit like this mastermind game that many of us played as teenagers. Okay? And this reformulation as a learning challenge allowed us a couple of years ago to prove 2 things. This learning challenge is easy if you have access to 2 copies of the state and can process them simultaneously. But it is exponentially hard for any conceivable single copy strategy, no matter what quantum evolutions you can do, and no matter how much classical coprocessing you can do. So easy for 2 copies, hard for 1 copy. And this line of work, I think, culminated in this paper that I'm very proud of called Quantum Advantage in Learning from Experiments, where we actually implemented this learning challenge on the Google Sycamore chip here in Santa Barbara and showed this plot on the left-hand side, where you can see that the two-copy learning strategy really beats this exponential scaling in the number of qubits, whereas one single copy strategy we use, classical shadows, really dies because it can't keep up with the complexity. Okay, so these are kind of like the stakes. Find a challenge where we can first show that it's easy for two copies and then prove that it must be hard for any single copy setting. Is there questions or comments at this point? So Emmanuel is asking how demanding it is that the two copies are actually the same. I think there's some stability in there. You can also do error mitigation. So I think kind of like this is actually, this is stable, I would say. But in order to give you an exact number, I would have to go back, look in the appendices and do some computations. But I think it's kind of like, because it's a swap test underlying, it's kind of linear in the perturbation, so I think it's not so bad. Great. Yes?
Words for two copies and one copies and the ON copies. Like the, I understand that either you have like two copies of the same
yes.
background at the same time for one copy, but you also need N copies. Right? So
yes.
Right.
So
like a different word, you know.
Daniel points out an annoying inconsistency in my use of language, because I use copies as kind of like in one time as how many copies do you need in parallel to run a protocol, but there's also the sample complexity, which asks how often I have to run that, which gives me the total number. So I would say the sample complexity is the total number of measurements I have to do. And if I have a k-copy protocol and need m samples, then the sample complexity is m times k. Thank you. Yes?
So this particular density matrix is a mixture of identity and one
yes.
poly string.
Yes.
Is this protocol also applicable when there are many poly strings with all different questions and you are asked to figure out all questions?
Excellent. Son Woon points out that this is a very particular construction of data hiding, and it only uses one poly word. Later in the proof, we'll actually use kind of like a statistical mixture of many of them, kind of like in order to cover it more evenly. I will briefly talk about it when I get there, about when we do the hardness proof. Okay, so now, how did we do this plot on the Google Sycamore chip? What is the two-copy protocol? And for me, this was kind of like the most beautiful part of this project, is the key insight behind all of this is that we know that n-qubit polyobservables either commute or anti-commute. And we have these canonical commutation relations that tell us sometimes it's plus and sometimes it's minus, and it only depends on the Pauli words. And for the single copy setting, this is bad news because many of them anti-commute, and so we can't jointly measure them. But if I take twofold tensor products of the Paulis, they all commute, because minus times minus is plus. So if I take kind of like tensor products of n-qubit polyobservable, I get a subset of all two n-qubit polyobservables that all jointly commute. And so there must be a unitary that transforms two n-qubits into an eigenbasis that jointly diagonalizes all these Paulis. And now you can see where two-copy access is empowering. Because if I measure now, perform kind of like this measurement, on row tensor 2, it allows me, because tensor products factorize, to estimate the square of all Pauli observables jointly. And this is also why I needed the absolute value. I go to the square, and I need kind of like I lose the plus minus information there. I only learn the magnitudes. And if you actually do this, sometimes life is beautiful. The circuit that does it is known as the destructive swap test or Bell sampling, and it's one of the easiest circuits you can envision. It is comprised of n C0 gates and n Hadamard gates. It's parallelizable and it has depth too. And this is the circuit we basically ran on the Sycamore chip. And the only thing that remains is kind of like this is a square, take the modulus and take the square root, and then you can jointly learn all magnitudes of Pauli observables. Yes? Can you start again, please? Yes. Yes. He is asking that this is a feature of qubits where we go to 2 copies. Whether you can generalize it to qubits, this is exactly my result. I'm going to do it later. Well, thanks for spoiling. Yes, and if you compute the sample complexity, you take the same data to compute all these Pauli observables, so you have the statistical dependence, but you can still do a union bound that tells you that the extra overhead you have to combat the statistical dependence is logarithmic in the total number of observables. The logarithm of 4 to the n is n, and what you pay is 1 over epsilon to the 4, because you estimate the square and then take a square root. And the square root makes errors larger, and so you kind of like you scale with 1 over epsilon to the 4. Okay? Yes, Maxime?
Is there a main contradiction that to store all these Pauli observables in memory, you require exponential memory, and you get them as a polynomial number of...
Maxime is pointing out that we only need a polynomial number of data to be able to estimate an exponential number of terms. And I think this is also the setting that I have. I view this as kind of like an empowered classical shadow, a data set that I have, and then whenever you ask me about the absolute value of a Pauli observable, I know I can predict it up to epsilon accuracy. But if I want to do it for all of them, it will take me a long time. But I know that the data contains all the information I need in principle to do so. Think of it like a compressed version, like really compression. So this, believe it or not, is the easy and fun part. You have to kind of like find a creative quantum solution to a learning problem. The hard part is to show that the same cannot be done fundamentally in a single copy setting. So this is where learning theory plays a role. And I don't want to kind of like go into the details here, because quite a lot of proof development went in it. But why is it conceivable that this Pauli learning is challenging for single copy strategies? And here it starts to matter what kind of data hiding states we use. Because if you look at this particular construction, you can see there's some, let's say, malicious intelligence behind it. Because if I compute the expectation value of this mixed state with any Pauli string, I get a Kronecker delta. So the expectation value is 0 for 4 to the n minus 1 Paulis, or 4 to the n minus 2. It's 1 for the identity, and it's 1 for the hidden secret I encoded. And so this is an all or almost nothing scenario. If you want to crack this without knowing my secret, it's a bit like having to crack a bicycle lock. You have to try through all the possibilities, because everything you learn is that the thing you tried is not the answer, intuitively. At least if we restrict ourselves to Pauli basis measurements. Now, the general setup is much more general. It allows for any unitary kind of like transformation and also adaptive learning protocols. But you can still turn this into a hardness result for arbitrary measurements by utilizing uncertainty relations between individual Pauli bases. Kind of like Pauli bases are mutually unbiased in the sense that you cannot learn anything about this direction if you do this direction. And so intuitively it shouldn't help you if you're somewhere in between. There are still underlying uncertainty relations. And this is what we use in order to argue that this shouldn't be possible for single copy measurements, because it would violate uncertainty relations. The actual proof is a bit harder. We first reduced the learning challenge to a many versus one distinguishing task. So we kind of like have two alternatives, either the maximally mixed state or a randomly selected state of this form. And then we can mathematically formulate any single copy strategy as traversing down a learning tree. And there's two options, either it's the null hypothesis or it's the alternative hypothesis. And if I traverse through my learning trees, I get different probability distributions at the leaves. And now you can, and this is actually nice, you can go back to results from the 50s by Lecan, who had what's called a two-point method, who pointed out that if you want to distinguish the two original options, you also have to be able to distinguish the probability distributions at the leaves. And the optimal distinguishing possibility is the total variational distance between these leaf nodes. And then you can relate this to another property. And ultimately to the depth of the learning tree. And if you do this, you can really prove that no matter what single copy strategy you do, for these tasks, you need at least 2 to the n over epsilon squared copies or samples in order to learn this. And this has been beautifully written down last year by Sitan Chen and friends in this very nice paper. It's been a long development, but this is, I think, kind of like the newest and coolest part. Are there questions or comments at this point? This is either very good or very bad. I pretend that it is very good. Now, let me move on to the main results of this talk and of us, which in a way you already predicted. Can we kind of like take the same setting and find d-copy challenges where you can solve it with d copies, where d is larger than 2, but you cannot solve it with d minus 1 or fewer copies in a similar setting? And one, I guess, obvious way to do that, because you already saw it, is we can go from qubits to qubits. Because maybe the 2-copy advantage had something to do with Pauli matrices are valid for qubits, and so kind of like 2 plays an important role. But there is a known canonical generalizations of Pauli matrices to higher dimensional Hilbert spaces. And it's these Weil-Heisenberg matrices that I guess most of you know about. Kind of like they extend the feature of Pauli matrices from qubits to qubits, and roughly speaking, Pauli X becomes a shift, modular addition by 1, because Pauli X maps 0 to 1, and 1 to 0, which is 2 modulo 2. And the Pauli Z matrix becomes a diagonal matrix with d roots of unity on the diagonal. Pauli Z has second roots of unity on the diagonal. And you get Pauli Y matrices by taking combinations of Pauli X and Pauli Z. And here's an example that I like about dimension 4. If you want to write down the basic Weil-Heisenberg matrices for dimension 4, a Q-quad, they look like this. And then there's 16 possible combinations of these. And they generalize useful properties. For example, there's always d squared, many of them. For dimension 2, this is 4. We have 4 Pauli matrices. There's also canonical commutation relations. And before, we had a minus 1, which is a second root of unity. For Weil-Heisenberg matrices, it becomes a d root of unity. And then, last thing is maybe easier. It's easy to extend these constructions with a tensor product to n qubits. So kind of like if I want to go to this many-body setting where kind of like the hardness really becomes palpable, I can just take tensor products. And the last important thing that will become important later is that these kind of like Weil-Heisenberg matrices have very different eigenbases. A bit like Pauli bases, X, Y, and Z are very, very different. They're mutually unbiased. And the Weil-Heisenberg matrices can also, some of them can be jointly diagonalized, but there's d plus 1 different bases that are also mutually unbiased under the condition that d is prime. So for composite dimensions, this becomes more difficult. But if we assume that d, the qubit we generalize to, is prime, then we also get d plus 1 distinct and unbiased eigenbases. For Paulis, this is true. We have 3 mutually unbiased Pauli bases. Marin?
These are no longer Hermitian Pauli.
Very good. Marin rightfully points out that these are no longer Hermitian. So how should I view them as measurements? Here, I extended them as unitary evolutions. I give you 2 answers. One of them is to just look at the symmetrized and antisymmetrized variant. I can decompose a general matrix into a symmetric and antisymmetric component and learn those. More generally speaking, I'm of the opinion that when we perform a measurement, what matters about the observable is that it is diagonalizable, because this gives us access to an eigenbasis, and this is actually the single-shot basis measurement we perform. And the eigenvalues we associated to it in classical post-processing is just kind of like a choice of us. So I actually am of the opinion that we can measure every normal matrix that is diagonalizable. But if you're happy with this, I will formulate the learning challenges always with the symmetric part. Yes?
Just to make sure I'm on the same page, that's typo in X, right?
Some what?
The X operator?
Yes?
Shouldn't have 1 at the bottom right corner.
It's a shift, right?
Yes, it's a shift. Sorry. Thank you, Sonwoon. Yes, you found a typo on my slides. It should be a shift. This should be somewhere else. It should really look like this. Thank you. And now, with these definitions in line, I can define a straightforward generalization of the Pauli learning challenge from before, which is the Weil-Heisenberg shadow tomographies challenge, where we jointly have to learn all symmetrized expectation values of these Weil-Heisenberg matrices. Okay? And nota bene, this is important for me because I'm at my heart a qubit guy. Everything I'm saying here can be transpiled into qubit systems. For example, if you work with a Q-quart, I can use 2 qubits to represent them, and then these Weil matrices will become entangling circuits, but kind of like the complexity doesn't explode. I will mention that later on as well. So how can we do it? How can we solve constructively n-qubit Weil-Heisenberg tomography? And the idea is very similar to what we had before. If you have an n-qubit system, I can jointly learn all d to the 2n Weil-Heisenberg observables in modulus by kind of like this is the goal. My reformulation again is one as a learning challenge because I need this as a framework. And what we can prove is that this challenge is easy if we have access to d copies. It's a very tractable protocol, and it's hard for any d-1 copy strategy. And for the constructive side, the key insight is really we have again a commutation relation, and now we have a d-th root of unity. And so we need the d-th tensor product to make them all commute, but then they do. And so you know there is a d-n-qubit readout circuit that jointly measures all of them. And sometimes life is nice, and it's really the qubit generalization of the swap test, as said before. So for Q-trit, for example, we now need 3 copies, and we need kind of like qubit extensions of the C0 gate and qubit extensions of the Hadamard gate. But the complexity is very, very small. And in the end, we take the modulus and the d-th root to get all the values we started with. And if we look at the sample complexity, we get something that is again linear in the number of qubits, but the accuracy suffers because we have to take d-th roots, which is to be expected. And then very quickly, this was the hardest part of our work. Can we prove that this strategy is now hard? This learning challenge is hard not only for single copy strategies, but for d-1 copy strategies. So we also have to take into account multi-copy strategies now, right? If d is 3, we have to prove that 2 copy strategies fail. But the underlying intuition is the same. With this data encoding, we again force the learner into a situation that if they do eigenbasis measurements of these generalized Paulis, that they basically learn nothing, and you have to measure many Weil-Heisenbergs there. And you can really, with a lot of work, you can extend this to generalized measurements on multi-copy protocols that are where the number of copies is smaller than the threshold, using uncertainty relations between these Weil-Heisenberg eigenbases. But we really need these uncertainty relations, and we only have them if d is a prime number. So this lower bound is now conditional on the number of copies we have being prime. And the actual proof strategy is an extension of this very nice framework to the setting where we allow for multi-copy strategies and these more generalized Weil-Heisenberg matrices. And it was a lot of work, and a big shout out to the lead author, Jan Möller, who made it work here. But it's very similar in spirit to the qubit strategy. And with that, yes? Yes. So Andreas asks if only d needs to be prime or if there's further restrictions. Only d needs to be prime. Only the threshold we look at needs to be prime, and then we can control all multi-copy strategies with strictly fewer copies. Yes?
How many powers do you need to do the double plus consolidator into a qubit system?
Thank you. He asks how expensive is transpilation into qubits. Right? Great. Couldn't ask for a better time. I have an example for the Q-trits here, where we did it kind of like explicitly. We start with a native Q-trit scheme to get kind of like a 3-copy learning strategy that is easy to solve with 3 copies on a Q-trit processor. And here you can see how it decomposes into qubit gates. And for a Q-trit, we need 2 qubits for each Q-trit. So kind of like the total number doubles. And the generalized C0 can be decomposed into kind of like 5 of these entangling gates. And the generalized Hadamard can be decomposed into this. In general, the overhead is logarithmic in D. If I want to represent a D-level system in qubits, the overhead is log D, and the same is true for these elementary gates. Fortunately, because the generalized swap test had such a nice structure. Yes?
How many powers do you need to qubit system to represent the
Okay. he's asking a very interesting question. How many qubit Pauli strings do I need to represent this, kind of like in the transpiled form? And the answer is, I don't know. It's a good question. We should look at it. Maxime?
If I elevate this question, does it mean that there is a density matrix in qubits which is not learnable?
Yes.
By this argument?
Yes. So Maxime asks that if he relays that and also kind of like transpiles kind of like the density matrix underneath, then we found a learning challenge that kind of like where the underlying density matrix is not, even the Pauli observables are not learnable with only 2 copies. They need 3 or more copies. Great. Thanks. And that's it. Kind of like, let me quickly wrap up. I'm of the opinion that this quantum enhanced learning with multiple state copies is powerful and timely. What I tried to kind of like carry across is we now know exponential improvements for several 2-copy protocols, for example, Pauli shadow tomography and purity testing. We also know exponential improvements for all copy protocols, like optimal quantum state tomography and Aronson's shadow tomography. And here we explored the vast regime in between by identifying learning challenges that are simple when you have access to D copies, but are exponentially hard in a provable way if you have access to strictly fewer copies. And our construction allows us to present and kind of like build such learning challenges for every D that is a prime number. And this gives us still an infinite hierarchy of multi-copy learning tasks because there's surprisingly many prime numbers between 1 and infinity. Thank you very much for your attention.
Thanks a lot for a great talk. More questions?
So she's kind of like building on the last question by Maxime. What happens if we kind of like transpile these problems into qubits, right? How does the hardness change? And kind of like what we proved here is kind of like here still, I think, kind of like to take our results kind of like seriously. We proved that if you have access to D copies, you can always do it, right? Kind of like this is one part here. And we also identified a subclass of quantum states that are hard to learn in this setting if we have access to D-1 or fewer copies. And I haven't thought deeply about this connection yet, but my first guess is that the family of states we have here, which are hard, is different from the family of states we constructed that are hard and easy for the Pauli shadow tomography case. Yes, but here we always kind of construct, for the hardness of learning, we construct this very particular combination of maximally mixed plus a Pauli string. And now here we have maximally mixed plus a Weil-Heisenberg string. And my guess is that if we decompose this in Paulis, we will have very many different Pauli terms. But I haven't verified this, but this is my first guess. The kind of like what is easy in the qubit realm, if we decompose it, it might become more complicated in the Pauli realm.
Yeah, more questions?
Yes.
Also many non-prime numbers.
Yes.
Do you have any guesses of learning tasks that would be how special that?
Very good question. Matteo rightfully points out that there's very many numbers that are not prime numbers. What can we say about that? Jan, actually the lead author of this paper, took kind of like an obsession there. And we have generalizations that hold for every square free integer, but it's kind of like a bit with reductions. But there is combinations of dimensions where I'm a bit worried. Like, for example, about 4 or something, I'm not sure. Because there we really don't have mutually unbiased bases, and I wouldn't know how to kind of like reduce them. But we have in the paper an auxiliary construction that shows that we can also generate learning tasks for every square free numbers. And now maybe it's a bit denser.
Yes. Pablo?
So the question is, what happens if we move to fermions And whenever I get this question, I embarrass myself by confessing that I don't really understand fermions. But I'm happy to discuss about this afterwards.
Sunran?
So do you have any application in mind, specifically any cryptographic settings or like quantum key distributions or certifications of blah? Is there any application?
So someone asks for applications. So far, no. But I think that this is maybe an indicator that multi-copy strategies could give you data sets, generalized classical shadows, if you will, that allow you to learn more about the system than a single strategy, copy strategy would. But I don't have a concrete kind of like application in mind. Another thing is also just run this and show that it works. Kind of like but kind of like concrete protocols I don't have in mind yet.
Are there more questions? Okay, maybe one or two final ones, or let's see.
So in continuous variable systems, like the D goes to infinity limit, there, can you do that task with finite number of copies?
Excellent question. The number we get, the exponential lower bound we get is d minus 1 to the power of n, which partly makes me unhappy because it doesn't cover the qubit case exactly, but it allows you to take both possible limits. So kind of like in the case where you let d become large and n small, you still have a lower bound kind of like on the number of copies, but the main scaling, the main exponential scaling we consider is this n, and so it really only becomes a strong separation if we have many of these particles. But large but finite dimension should be fine.
Thanks. Okay, there's one more. Yeah, no, go ahead.
Sorry. Yes. Excellent question. She's asking about, this is only about the magnitudes, what about the signs? This is like an exciting development over the last couple of years. Kind of like we had some initial ideas where we just say kind of like do this first, then you can order all of them by importance and truncate and then just sequentially measure, which generically works because it's impossible for many poly observables to be big. And recently, Robbie King and the Google team had like a really elegant extension called triply efficient shadow tomography, where you kind of like extend these ideas in order to also have a sample efficient strategy to learn the science. And I think it's totally possible to generalize this to this setting, but we didn't do it yet.
Maybe last questions in the back? Oh, same question. Okay. Any last one? Okay. If not, then let's thank Richard and all the speakers of the session.